So by talking among yourselves, you are not only discouraging your, not only discouraging the speaker, you are discouraging your own teachers. So don't do that, please.
So should I speak through? Okay, yeah, I can speak through this. A very good afternoon to all of you. I'm quite honored to be here in Karnataka University of Dharwad. I have come to this campus probably twice before, but this is the first time I'm inside any building and I'm facing an audience who is going to listen to me. So my name is Amlan. I'm working in the Department of Mathematics of IIT Dharwad. I work mostly in the area of fluid flow and computational techniques in fluid flow. This is basically a joint work with some of my collaborators. So some of them are in China and some of them are in US. Our story starts somewhere in England, in mid-19th century England. So there used to be a person whose name is Henry Selby Hillishaw. Okay. Now, just try to imagine yourself in mid-19th century. This is perhaps one of the best period in their history. So they are actually dominating all the sea lanes. Most of the trades are happening through them. And at the same time, we can see that science and technology is also flourishing in this country. Okay. In particular, in the area of fluid mechanics and physics, they are actually doing amazingly well. So James Clerk Maxwell, for example, has written down the laws of electromagnetism, which we still use. Okay. In fluid mechanics, there are people like Reynolds. There is Gabriel Stokes. So Stokes, the name Stokes, famous for, is associated with the Navier-Stokes equation. Then Osborne-Reynolds, you must have heard, if you have taken a course on fluid mechanics, you may have heard about something known as Reynolds number. So that's due to Osborne-Reynolds. And then there is this another person whose name is G.I. Taylor. So all these people are kind of related to this mid-19th century era in England. And about our main character of this story, that is Henry Shelby Hillishaw. So he was born in Essex, England, and he used to work in University College, Liverpool for a large part of his career. He was a very famous engineer, and he used to work also as a research scientist in the area of fluid mechanics. Okay. Very accomplished career. He was made a fellow of Royal Society. He was also a member of Royal Institution of Mechanical Engineering, etc. He has made fundamental contributions in designing ships as well as aircrafts. Okay. But we are not going to talk about any of his other achievements, but we are going to focus on a particular class of flows which he himself observed, and since then that particular class of flow has come to known as the Hillishaw flow. Okay. So we are going to focus mostly on this particular work of Hillishaw's career. Okay. So what is basically a Hillishaw flow? So in the Hillishaw flow, what happens is that imagine that you have two plates which are very close to each other. How close I will tell you. And you can imagine that there is fluid trapped between these two plates, and this fluid is flowing. So the Hillishaw flow is all about capturing this flow which takes place between two very closely placed plates. Okay. So suppose if you look at the gap distance, so this B stands for the gap between these two plates. Imagine that this B is in the direction of Z. Okay. So how big this B can be? So this B is actually even a fraction of millimeters. Okay. So the typical length scale for this B is something around like 500 millimeter to 200 millimeter. So I'm not even, sorry, 0.5 millimeter to 0.2 millimeter. So I'm not even talking about millimeter scale geometry. I'm talking about something a little less than even millimeters. But if you think about the length scales in the XY plane, so in the Z direction, I'm dealing with fractions of millimeters. But if you are within the plane, then in the XY plane, I'm dealing with something which is in the order of several centimeters. So suppose you have 5 centimeters, which is in the XY plane, and you have say 0.5 millimeter in the Z direction. So if you take the ratio of this L, which is a characteristic length scale in XY plane, and if you divide it with this B, then you would see that L divided by B is nearly in the order of hundreds. So the length scale in the XY plane is 100 times more than the length scale in the Z direction. Okay. So why is this flow important? So these days, this flow has become extremely important because of its connection to something known as microfluidic devices. What are microfluidic devices? So microfluidic devices, an example of it could be a lab on a chip. So what is meant by lab on a chip? So from the name, you can perhaps infer that it's an electronic device which is of chip size. Okay, so it's small, but it can perform tasks which large-scale laboratory devices do execute. So that's what is called the microfluidic device, the lab on chips. So these lab on chips kind of devices have become very popular nowadays because they have applications in biology, forensic sciences. So in forensic sciences, for example, if you want to understand the trace of blood, then some of these microfluidic devices can do the job for you. Okay? And the most important thing is that these microfluidic devices, most of them operate with very little amount of fluid. So, because again in these microfluidic devices, you can imagine a very little amount of fluid is trapped between say 2 plates, the application of the Hilly-Shaw flow comes into picture. Okay? So that's the main reason why these have become so popular, this kind of flows have become so popular nowadays. Any questions or comments so far? So you understood, right? I have 2 plates which are very close to each other, and there is a fluid which is flowing in between these 2 plates. I want to capture the dynamics of this fluid flow. Okay. Now, what are the types of geometry where people study the Hilly-Shaw flow? So there are 2 dominant kinds of geometry in which people actually do study the Hilly-Shaw flow. One is called a rectangular channel. Okay. So in the rectangular channel, what happens is you literally have a rectangular region through which the fluid is flowing, and one part of the rectangle is filled with one particular fluid, the other part of the rectangle is filled with another fluid of a different viscosity. And what we want to do is, we want to study the interface that separates these 2 fluids. One of the fluid will be more viscous in nature, the other part of the fluid will be much less viscous in nature. So what we want to understand is how the interface between these 2 fluids are evolving in time. Okay. So that's what is the rectangular channel configuration. The second possible configuration is the so-called radial configuration. So what is a radial configuration? In the radial configuration, what will happen is you will have a fluid drop that will be surrounded in all possible directions with a second fluid of contrasting viscosity. So if you are wondering what they look in reality, then this is how they look. So needless to say, this is the channel version of the Hilly-Shaw problem, and this one is the radial version of the Hilly-Shaw problem. So I have one fluid, for example, over here, another fluid over here, and this is basically the interface between this fluid and this fluid. And as you can see that we have deliberately drawn it in such a way that the thickness of the fluid over here, if you look at the thickness, that thickness is much smaller than any of the length scale here or over here. So the thickness is really, really small. The same holds for this problem also. So here you have one particular fluid which is occupying this gray region, and outside this gray region you can't see it, it's almost white. There is this another region where there is a second fluid, and again what we want to do is we want to track the interface. So this interface which separates this fluid and this fluid. So that's what we want to do. Okay? All right. So I took up these images from the internet, and the next thing that we want to analyze is what drives the fluid inside either this geometry or inside this geometry. what is the driving force over here? So that's where actually the Hilly-Shaw flow takes its various forms. In the classical form, that is the most common form, that is the most well-studied form, what happens is you inject, see you have this arrow over here which is pointing downwards. So what we do is we inject this fluid into the system from outside. So the force of injection or the injection itself actually is something which is driving the interface between this fluid and this fluid. Okay. Now, this injection problem was actually studied by very famous fluid mechanics people, Safman and Taylor. They investigated this problem. Then later on, Patterson, Chain, they also studied this injection problem. So what happens is that the injection problem, if you have a less viscous fluid over here, and if you have a highly viscous fluid over here in the outer region, then this injection problem is very unstable. What do I mean by unstable? So you see this interface between this region and this region. So what happens is the interface starts to develop as you push more and more fluid into the system. The interface starts to develop fingers. Okay. And not only the fingers, I mean, there are some primary fingers which will penetrate this more viscous fluid from this less viscous fluid region. This tips will, so these fingers will also undergo splitting. Okay. So the fingers are growing, and after some time on, the fingers will also split. So that's the instability associated with this particular problem, where you inject less viscous fluid into a highly viscous fluid in a Hilly-Shaw setup. Okay. So this problem you can study both in rectangular and in radial geometry. And let me show you one of the results that was obtained via simulation. So how things happen in time. So what can you expect from the shape of this interface as time progresses on? And it looks something like this. Okay. So what's happening over here? Let me try to explain you what is happening over here. So at the beginning, the inner interface is over here. Okay. So the innermost interface at time t equal to 0 is this very simple blob of fluid. Now you are injecting the fluid into it. This blob starts to grow. So some of the initial interfaces are given over here. But as the time progresses, as you can see, fingers start to emerge. So I call these as fingers. Okay. So these fingers start to emerge on the interface. And as the time progresses further, these interfaces, these fingers, they undergo something known as tip splitting. So here, for example, there is a tip splitting at this particular stage, and this has become one branch of the one branch, and this has become another branch. And then later on in time, you can see that this branch is undergoing further more splitting themselves. So these are some of the small fingers which are actually developing on this primary finger. So these are secondary fingers which are developing. So these, you can also call these as secondary fingers. These fingers are developing in the primary fingers. Okay. So this is basically a simulation result. This is not something from the experiments, but even in the experiments, you actually do see this kind of structures. So simulation here is very good in capturing what happens in the experiments. Okay. Okay. So this was the classical version of the problem, which is driven by the injection of the fluid into the system. So what else can drive the fluid flow? So another thing that can drive the fluid flow is when you have one of the two plates static and you start to lift the other plate. Okay. So remember, you have two plates which have very small thickness among them. In the classical version, you inject the fluid, but you don't play with the plates. But in this lifting version of the problem, you keep one of the plates fixed, and then what you do is you lift another plate. Of course, you do it in such a way that you do not lose contact with the fluid. If you lose contact with the fluid, then nothing, I mean, this is no more a problem that we want to discuss, but you are lifting the plate by maintaining the contact with the fluid. So this is how again the shape would look like. So this is something at the time, initial times, okay? And you can see that, now imagine that you have a certain volume of a fluid and you are lifting the plate. So what will happen is the thickness of the fluid is increasing, but you are not injecting any fluid from outside, which means that the volume of the fluid should remain conserved, okay? So the volume of the fluid should remain conserved, and if at initial times the interface between the fluid and the surrounding looks something like this, at later times you can see that different patterns are emerging, and finally this is again a simulation result. When the simulation stops, the shape of the interface looks something like this, okay? Of course, the patterns that you see over here, the fingering patterns that you can see over here are completely different from the fingering patterns that you observe over here, okay? All right. So what else is there? What else can drive the fluid motion? The next thing that can drive the fluid motion is when you start rotating the system. So this time you are not injecting the fluid, you are not lifting the plate, rather than you are taking the whole system and you are rotating it. So if you start rotating the system, then you can understand that the centripetal force, centrifugal force, all these things will come into action, and they will again result in the instability of the fluid interface, and this time you can see that various kinds of shapes can emerge depending on the viscosity contrast, okay? So I think in this direction what they have done is they have taken fluids with different viscosity contrasts, and in this direction they have changed the rate of rotation. So you can clearly see that again here is also a problem where the interface is unstable, but the fingering patterns, especially for this problems, is quite different from the fingering pattern of this problem as well as this problem, okay? So fourth driving force. So what you can imagine is that there is a pressure difference between two interfaces where the fluid flow is taking place. So this problem has been investigated very recently by this Australian group, okay? And I have not put up the results because you understand the philosophy by now. All I want to do is I want to study the dynamics of the interface as the time changes on. And what I'm trying to do is I'm trying to tell you what kind of forces are there which can actually modulate the interface. So pressure difference is another thing. Then apart from that, what people have done is people have done investigations by taking ferrofluids and applying the magnetic forces. So what are ferrofluids? So these are fluids in which these have electromagnetic properties. So you can use an external field. If you have a ferrofluid, then what you can do is you can impose an external electrical field in order to make the flow happen. Same goes for the magnetic force. Then what you can do is you can actually structurally tweak the problem. For example, you can take tapered geometry. So instead of taking two plates which are at uniform distance from each other, what you can do is you can change the length of the gap from one place to the other, and that's called a tapered geometry. So people have studied also the motion in tapered geometry. So these are different kinds of driving force that drives the flow in the case of Hilly-Shaw problem, and this is how pretty much the game is played. So in this area what people do is people use multiple physics which are relevant for the problem. They apply those physical fields onto the basic problem, and what they do is they study the interface. Okay, all right. Achha. So now a little bit of math. I will not go too much into the math because I thought that it's boring. I mean, you always do classes and all that. I don't want to again show some equations, but this much you have to bear with. So. So what we start with is this Navier-Stokes equation. We don't have the gravity term. Of course, you can see that there is no rho g kind of a term, g kind of a term over here. We have time derivative of the velocity field. This is the convective part. this is the force due to pressure, and this is the viscous term. Okay? And of course, on the top of that, you need to have the equation of continuity or the mass conservation law. And then in the Hilly-Shaw flow, what we will start doing is, we'll start analyzing which term is relatively more important as compared to the others. So we are not going to work with the full Navier-Stokes equation. What we are going to do is, we are going to write down a simplified version of the Navier-Stokes equation, and we are going to play with that truncated version of the Navier-Stokes equation. Okay. So the first assumption that we make simplifies things a lot. So we are assuming that the time derivative of the velocity is 0. That means in time things are happening very slowly. And we also assume that the third component of the velocity is equal to 0. So in this equation, I immediately kill off this term, and from the rest of the terms, I hypothesize that the velocity V3, the velocity component V3 is equal to 0. So if you apply those assumptions, then what remains in this Navier-Stokes equation are these terms. Okay. So mu is the viscosity of the fluid, and rho is of course its density. You know all of this. So this is what is a truncated version. Particularly look that this equation simplifies a lot. Most of the terms are gone over now, and you can clearly see from this equation that pressure is basically, if you take the derivative of pressure in the vertical direction, then what you get is 0. Can anybody identify what these boundary conditions are at x1 equal to 0h and x3 equal to 0h? I say v1 and v2, these are 0. So this is basically our no-slip boundary condition. And if h is very small and the flow happens very slowly, then what we also assume is that the derivative of Vy with respect to xj for I and j equals 1 and 2 are also very, very small. Okay. So I'm making drastic assumptions over here, and with this kind of simplification, I can get reduction of further terms over here, and I'm finally laid with these very simple looking equations given in this slide, where the partial of pressure with respect to x1 is given by this proportionality constant mu times the second derivative of v1 with respect to x3. The partial of pressure with respect to x2 is also given by mu times the second derivative of v2 with respect to x3. And from the last equation, we can clearly see that the pressure must be independent of the coordinate x3 itself. Okay? So very simple equations I have come down to. And once you take these two equations, you integrate them, then what you get are the expressions for velocity component v1 and v2, which is given over here. And then what I do is, I average this velocity v1 over the thickness to get this velocity v1 tilde, which is given over here. It's quite simple. And same for the velocity, the average velocity component v2, which is given through this equation. All right. Now, if you just look at these equations, that is the average quantities v1 tilde and v2 tilde, then you can clearly see that the right hand side is nothing but the divergence of the pressure. So using that observation, I can write that v tilde is nothing but minus of h squared divided by 12 mu and the gradient of pressure. And as before, we still have to retain the divergence free condition. So the divergence free condition tells me that the divergence of the velocity field, this v tilde, is going to be 0. So if you plug this v tilde into this particular equation, then you are finally led to this relation that the pressure P, if you take its divergent, it is going to be equal to 0. So this is the basic governing equation for the Hilly-Shaw problem. The pressure in the Hilly-Shaw flow is going to be a harmonic function. Okay, so it's harmonic function. That's what is important. If you have a pressure which is in the Hilly-Shaw fluid, then the Laplacian of the pressure is going to be equal to 0. Okay. All right, so this much for the basic problem itself. Now, what I'm going to do is, I have some equations now, and now what I'm going to do is, I'm going to see what kind of technical analysis I can do on this problem. So what kind of mathematics can be done on this problem? Okay. Now, as it turns out, this is an interfacial phenomenon, right? So I have two fluids. One fluid is in green and the other fluid is in white in the outside region. And in the interface, these two fluids are interacting with each other. So it's an interface problem. So if you are looking into an interface problem, everybody knows that you have to consider surface tension. So in a free interface, surface tension will always act. Okay. But sometimes what people do is, as a part of mathematical idealization, even in this interface problem, sometimes people actually drop the surface tension. They simply ignore the surface tension. If they ignore the surface tension, then the problem that we deal with is actually known as Laplacian growth problem. Okay. So remember, your pressure is harmonic, and if you have done a little bit of complex analysis, then the complex analysis tells us that the real and the complex part of an analytic functions are also harmonic. So by connecting these two things, these two people, Polubarinova and Galin, so they are Russians. So what they did is they invented a conformal mapping approach through which they could solve the Hilscher problems when surface tension was absent. Okay. So roughly in this conformal mapping technique, what happens is they have a reference domain, which is typically a disk. So from their domain, they create a function, one-to-one onto function, which maps to this reference domain. And using this mapping, what they can do is they can solve the problem which was on the original problem on the disk itself, and then use the same function to transfer the solution from the disk to their original domain. So that's what is roughly the conformal mapping approach. And pretty much, so this work was done in and around 1940s. Okay. But pretty much this technique has been used for almost all the analytical computations that happen in this domain, especially when you don't use surface tension. So people later on use this approach, and they solved tons of problems, Hilscher-like problems. So in particular, there are people like Sam Harrison, then Richardson, and there are many more. Actually, I cannot name all the people over here. So they all took this conformal mapping approach and gave a plethora of solutions of Hilscher problems. Okay. But then there is this second issue where you cannot ignore the surface tension effects. Okay. So in real fluids, you really cannot ignore the surface tension problems. And as soon as you plug in the surface tension, the conformal mapping approach becomes virtually impossible. This is because the equations that you get from this analysis of Polubarinova and Galin, they cannot be solved anymore as soon as you throw in the surface tension. So what people usually do is then they abandon that approach of complex analysis, and they take up something known as linear or weakly linear analysis, and then finally they move over to nonlinear simulations. Also, of course, there is theoretical PDE analysis also available over there. In the theoretical PDE analysis, people analyze the short-term existence uniqueness question of this kind of problems. PDE-based approaches, that's are also quite fine. But the other way to solve or to look into this problem is to do a linear and weakly linear analysis and then go for a full nonlinear simulation. So what is linear and weakly nonlinear analysis in the context of the Hilscher problem? So what happens is, if you have a Hilscher problem, then these equations are not very difficult to solve if you have a nice geometry. So for example, if you start with a circular interface, then what you can always do is you can find the solution for the problem, and then what people do is, instead of taking the circle, they perturb that circle using sinusoidal mode. So initially the interface is circular, so small r is given by capital RT, then they can solve the problem exactly. But then what they do is they add to this a small perturbation. So this epsilon is a small quantity, this delta t is a time dependent amplitude, and they use a cosine n theta mode on the top of this r theta. So basically they are perturbing a circle. So if they perturb the circle, then they assume that the pressure in this new domain, so the new domain is given over here, then the pressure of the new domain also has an asymptotic expansion, which is of the form P naught plus epsilon P1 plus epsilon square P2 and so on. So this epsilon corresponds to exactly to this epsilon over here. Because the interface is slightly perturbed, the pressure can also have a small perturbative expansion. So what people do in weakly and so in the linear analysis and weakly nonlinear analysis is that they know P naught and they try to find what is P1 and P2. Okay. So as I said, P naught is found already from the trivial problem when I have small RT is equal to capital RT. If you throw in this extra bit of stuff over here, then the subsequent terms P1 and P2, these two can be found out following the principles of linear and weakly nonlinear analysis. As it turns out that the linear term, so whatever comes from considering this P1, if you can find this P1 out, then the information that you can get from this P1 gives you the understanding of the roles of various physics that you impose on the problem. So for example, if you have a rotation, then the linear analysis will predict what will be the behavior of the rotation on the dynamics of the problem. So I have given one example over here. So if you do this linear analysis, you can actually show that surface tension tries to it tries to impede the growth of the perturbation. So surface tension is good in the sense that it wants to keep a stable system stable. On the contrary, the same analysis tells you that if you give a rotation onto the problem, then the rotation has a very destabilizing interface. It actually promotes the growth of the fingers. I have 3 minutes, okay. All right. So these analyses are only valid till the time the perturbations are small. Okay. So then to the discussion of the nonlinear simulations. So I think I will not go too much over the slides. I will try to actually explain you how what happens in these nonlinear simulations, and I will close my discussion over there. So in the nonlinear simulations, the biggest challenge is that we have a moving boundary problem. So in a moving boundary problem, what happens is the domain of the fluid keeps on changing continuously. So any grid-based method like finite element or finite difference, they break down. So what we do instead is we transform the PDE-based problem into an integral equation-based problem, and we solve those integral equations. Okay. How much time do I have?
2 minutes.
2 minutes, okay, fine. And then the second challenge in the boundary integral simulation, I mean in the simulation of this sorts is that you have a time component in your simulation. So your time step and your spatial grids are related by this relation. So if you choose a small delta x, you have to remember that this delta x is less than 1. So when you choose this delta x to be small, delta x cubic is even smaller than delta x, and your delta t has to be in the order of delta x cubic. So that means that you have to choose really, really small time t in order to do the simulations, and this is really bad. Okay, yeah, I will just finish over here actually. I had some more slides, but I will skip. So this for a very long time was a very bad bottleneck for Hilly-Shaw problem. But this problem was eventually solved in 1993 by these three people over here. Thomas Howe, who is in Caltech, Leo Perry, who is in University of Minnesota, and John Lowengrove, who was also in University of Minnesota. So these three people actually came up with a very special time-stepping technique which improved the stability constraint from this one to this one. Okay, so now this is much more better because delta t has to be in the order of delta x. Earlier, if you reduce delta x, then you had to drastically reduce delta t, given that delta x was small. So with this, I think I will stop over here. So using all these numerical methods, this simulation was conducted by a student of John Lowengrove, and that student happens to be my advisor. So that's how I got connected to this particular problem. So I will stop over here, and I'm happy to take any question that you guys have in your mind.
Thank you, Dr. Baru. So the floor is open for discussion and questions. We can have one or two quick questions, especially from student community. Do you have any questions? Okay, I have a question. Okay, so you said that if you include surface tension, that will create more problem.
Yes.
I mean, so can you just include it as a kind of a damping scalar function?
Damping scalar function.
Because as the fluid moves radially, you can include it as a kind of constant radial, damping function.
Okay, I think I should correct myself in a way that, surface tension as a physical force should actually be a part of the problem. The only issue is that if you include the surface tension in complex variable approach, that makes the equations difficult. That doesn't mean actually that we should ignore the complex variable, we should ignore the surface tension into the problem. You have to do it. Now in the context of complex analysis, whether your approach would make it a little bit easier or not, that I'll have to think a little bit. I don't know on the top of my head.
Any other question? Okay, I have one more question. So when you have magnetic forces or something,
yes,
how do you define the force field? Do you think that the force with which the fluid is moving and the magnetic force field, are they additive or?
Actually it is considered as an additive force, because if you don't consider it as an additive force, then it will be very complicated. You will not be able to deal with the equations very easily. Yeah.
Good evening, sir. By taking tension into consideration, solving problem by using conformal transformation is virtually impossible, sir.
I couldn't hear you very well. So,
by taking surface tension into consideration for solving the problem,
yes,
the conformal transformation using is virtually impossible, sir.
Yes.
Can you just justify it, sir? Because we are unable to understand it.
I think what happens is that you can still write down the Pauli-Barinova-Gallin equation. That is not a problem. But the problem is to find out an easy solution for it. So if you don't have the surface tension, then it is easy to find out the solution. As soon as you include that, you can still write down the equation, but it is difficult to find out the solutions. You have to again go back to the computers and find out computerized solutions. You won't be able to find out an analytical solution. So that's where the problem comes from. No, I don't say so. It's not a question of real line. The point is that you cannot find a closed form solution. You cannot write down the solution in a closed form formula. Otherwise, what you can do is you can actually have an equation. You can still have an equation which you will have to solve using computers. So numerical techniques again will come into picture.
If there are no questions, let us thank Dr. Baru for the excellent talk.
Thank you. Thank you very much.
Thank you, Kiran Kulkarni, sir. Now I request all the dignitaries to felicitate Amlan Bora sir. Thank you all the dignitaries. Now I request Kiran Kulkarni sir to chair the Srinivas Kulkarni sir.
So myself, Kiran, and Dr. Baru, we are the okay. So myself, Kiran, and Dr. Baru, we welcome you in this session. I also welcome the online speaker, Dr. Srinivas Kulkarni.